Thank you. Welcome everyone this afternoon. So this presentation will indeed be about UV filtering and UV selective PV devices, which is part of the TECH4WIN project. And for these devices, we have three partners involved. That's IMEC from Belgium, IREC from Spain, and Kenosystec from Italy. IMEC and IREC are more doing the material development and the device development, while Kenosystec is challenging us to make sure that everything we are doing is indeed industrially viable. So all choices we make that we take into account industry viability on the long term. So this top view picture you already have seen. The idea in TECH4WIN is that we have a UV selective cell at the top and an infrared selective cell at the bottom. The infrared selective cell at the bottom is typically an OPV that we're aiming for, which means that for the UV selective cell at the top, we would like to have a very good UV filter and try to absorb as much UV as possible. So one of the targets we have that you can see here on the left in the circle is UV filtering more than 99%. Next to that, of course, the visible and the infrared spectrum parts should reach the bottom cell. So we're also looking at the same, and it should be transparable as possible. So we're aiming for an average visible transmittance above 60% for our top cell, which means that we're having a quite difficult band gap perspective target as well. We're aiming for a band gap of at least 2.7 electron volts, so that we absorb the UV part before 450 nanometer. That's what we started with, or what the aim was at the start of TECH4WIN. Ideally, we believe we can go for efficiencies even to 2.5% on the long term. However, at this moment, our short-term target is to aim for 1%. As you will see, we're getting close, and hopefully we get very soon this 1% that we can move on to the next step. And all of this is scalable. So the sizes, the areas Alejandro already mentioned a few presentations ago, we are currently upscaling this device already up to 5 by 5 square centimeter, and we probably even have to go a bit larger. We have two approaches, chalcogenides and oxides in this case. So both of them are critical raw material free approaches. The chalcogenide approach is the focus of IMEC, and the oxide approach is the focus of IREC. I will start with the zinc sulfide selenide chalcogenide approach, on which we have been working on quite a lot for the last 2 years. Same thing for the second technology I will look at, the zinc oxysulfide, also something we started from the beginning. And then I will finalize my presentation with something new we have been doing, where we have been integrating a very thin amorphous silicon layer in the zinc oxide approach, which also has some advantages. So I will go through these three different approaches and give you some results, typical results that have been published, so you can have a look later on at the details if needed. The zinc sulfide selenide approach. So at the left, you see the fabrication process, a sketch of the fabrication process we have. So we started with zinc sputtering or evaporation, which we are then selenizing / sulfurizing in H2SE, H2S, to get our zinc sulfide selenide. And on the right, you already immediately see the transmittance, where you can see that zinc selenide has the lowest band gap, around 2.6 electron volts. Zinc sulfide has the largest band gap, around 3.6 electron volts. And the mix we are making, the zinc sulfide selenide we are making for the moment, has a band gap of around 3 electron volts. That's what you also see in these curves. You see the glass reference. You see indeed that the zinc selenide has the lowest band gap. You see indeed that the zinc sulfide has a higher band gap, and you see that we're somewhere in between. Absorbing very well the UV parts, leaving through as much as possible visible and also infrared. For the moment, the thicknesses of material we are optimizing is around 1 micron, so still quite thick because of optimization device reasons. Of course, we will have to reduce that thickness later on to become even more transparent. But it's already quite transparent, which you can see here. So the zinc selenide was the lowest band gap, 2.6 electron volt. So it's still a bit yellowish, as you can see. Zinc sulfide, 3.6 electron volt. That becomes quite well transparent. Still some grayish because of the thickness, 1 micron. And then the combination zinc sulfide selenide is somewhere in between. We see still a little bit of coloring, which we believe we can just reduce by reducing the thickness later on, if possible. It's not so easy to make these materials, as we figured out. On the left, you see a SEM top view picture. And what we figured out is during the salinization / sulfurization, the zinc partial pressure is quite high, which, because of that reason, we believe that we are easily making some holes, as you can see here. And these holes can be very clearly seen if we make cells in shunting paths. So we have to avoid it. We have been able to avoid it in the meanwhile for the thick layers, as you can see on the right, the middle SEM top view picture, where we have been playing with some pre-annealing in nitrogen, and we also have the ramp up for the salinization sulfurization was also very fast in that case. And then we have to be able to avoid it. However, I also have to be honest, for the thinner layers, it seems to be even more difficult. We did already do some process optimization, but we still even have to do more. Still, where are we? At the right, you see a first JV result for a thick zinc sulfide selenide layer. And you also see here copper doped. Indeed, if we make pure zinc sulfide selenide, then the conductivity is quite low. So typically we are even doping the material with some other material, with another element, like for example here copper, which is increasing the conductivity at least threefold. So for this solar cell structure, FTO, IZO as a protection layer for the FTO because of the salinization, and then at the front, nickel oxide and a very thin silver layer, we're having this JV curve. Good news is we have a solar cell, but as you can see, the photocurrent is very small. But as you will see in the next part on the zinc oxysulfide, we see ways on optimizing this photocurrent. Still, where are we for the zinc sulfide selenide? We do have efficiency of 0.1% for the moment, having an AVT of 55% at least. So at least it's promising, which has been submitted to Solmat and should be able to be read very soon, hopefully. Zinc oxysulfide. So there we are using sputtering of mixed targets, zinc oxide and zinc sulfide mixed targets. And you see here the cross section of all the different layers we are using. And you also see the band diagram, where you already see that as an electron transport layer, we are using C60. And the C60 also has the smallest band gap. So we have to be careful with the thickness of the C60, not to reduce transparency too much. The zinc oxysulfide itself has a band gap somewhere between 2.7 to 2.9 electron volt. The higher the sulfur, the more the transparency. But you will see the best devices indeed have been made for 0.6 sulfur content. And this BCP is still a whole blocking layer, which we have been using as well. You already see some transparency, some transmittance results comparing to the FTO layer. And you can clearly see indeed that this C60 layer for the complete devices, that the C60 layer is reducing transparency transmittance a bit in the visible parts, as expected due to the band gap. Still, UV filtering, quite good. Visible transmittance, quite good as well, as hoped for, which you can also see for the cell with the C60. You see the cell here on top of an IREC logo, and you can see it's very nicely transparent in the visible part of the light. So material characteristics. Here you see some Raman spectroscopy measurements indicating that this 193, this is zinc oxysulfide, that we indeed have the mixed phase. Then you also see the zinc sulfide and the zinc oxide has been shifted to 473. And from that shift, we indeed can calculate the composition, and we indeed see that the sulfur is around 0.6, so around 60% sulfur. So that makes all sense. You also see some SEM pictures, cross-section and top view. In the cross-section, you see that all the layers are well defined and quite smooth. In the top view for the zinc oxysulfide, you see some clusters of some nano-sized clusters, kind of. But you also see a very compact layer, so that seems to be quite good. And for the C60, this seems to be quite porous. So that could be probably optimized and even maybe thinned down if we think about the C60 absorption that we have for the moment. So there's room for improvement, but it doesn't look too bad. If I get now to the cell results, we see here cell results for two different devices, one with the C60 and one without the C60. Without the C60, the result we see is very similar to the zinc sulfide selenide, so a very low photocurrent. Indeed, a photocurrent of 0.11 milliamp per square centimeter. And bringing in this charge transport layer, this electron transport layer, the C60, is increasing the current and the VOC substantially. Someone's mic is not muted, I think. So
Bart, I'm sorry, you're muted now.
so thank you, someone muted me. Okay, I go back. Almost there. Yeah. I'll also use my pointer. So back to the JV results, with and without the C60. And with the C60, you see it's clearly improved, and we're getting a 0.5% efficiency for the moment. Having at the same moment an AVT of 69%, so above what we were aiming for. Still, there is room for improvement. You see some voltage dependent current collection in reverse bias. You see some S-kink shape here as well, probably some barrier layer somewhere in between all those layers. So clearly things can be improved. Same thing that we can say from the EQE, things can be improved. And indeed, for the zinc oxysulfide, we are investigating all kind of charge transport layers, both for the holes and for the electrons in the meanwhile. And we are also improving the zinc oxysulfide itself, because this was sputtering, as I already said. But we are looking in atomic layer deposition, where we believe we should be able to make a more conformal, better quality layer, maybe even thinner layer, but still the same transmittance. So looking into it. This has been published already in RLL Solar. So if you want to have a detailed look at what I went through quite fast, you can have a look at RL Solar. And then end of last year, we got an extra idea based on this nano energy paper in which they used amorphous silicon embedded between zinc oxide and nickel oxide, where the amorphous silicon, a very thin layer, 15 nanometer, as you can see, increased the performance because the carrier correction improved and also for longer wavelengths. And that's also what you bit see for the transparency. Bringing in this amorphous silicon layer is reducing the transparency a bit, of course. But still, they had some very interesting efficiency results. So we were thinking, okay, why not giving it a try? So we put amorphous silicon between our zinc oxide electron transport layer and moly oxide hole transport layer. And then we also optimized in the first instance the thicknesses of all of it. So for the amorphous silicon, we had a look at 15 and 30 nanometer, as you will see on the next slide. For the moly oxide, we optimized up to 25 nanometers, and for the zinc oxide, up to 400 nanometers. Here you see this optimization in the middle. Zinc oxide, we already used the best one, which was around 50 nanometers. And then you see that JV characteristics are improving for the thicker amorphous silicon layer, as you might imagine. So the 30 nanometer, we're getting better current and a bit better VOC as well. And also for the moly oxide, it seems the thicker moly oxide is giving the best results for the moment. What do we have? We quite easily in the first run, we got to a 0.5% efficiency with an AVT of 41% in the case of the 30 nanometer of amorphous silicon. Because indeed, if you look at the transmittance again, where we put again the FTO as a reference, and then you see two cells, one cell with 50 nanometer of amorphous silicon in red, so the higher transmittance, and one cell with 30 nanometers of amorphous silicon in pinkish magenta, I guess, which is a bit lower transparency, which is indeed is 41%. The other one is above 60%, is 64% for the AVT. And even for the TIC one, it looks quite well visually, as you can see here again, on an IREC logo, where you see it's very well transparent. This will be presented in November, beginning of November, on the C Future PV conference in EPFL in Switzerland. And in the meanwhile, of course, we will try to publish as well. So to summarize, in TECH4WIN, we are working on chalcogenide and oxide-based approaches for fully transparent UV-selective and UV-filtering PV devices. So we're aiming for very high band gaps, above 2.7 electron volts. In the case of the zinc sulfide selenide, we have been achieving a first efficiency, having also an AVT of 55%, having some issues typically with hole formation in the layers. But if we could solve that, basically bringing in charge transport layers, we should be able to increase the efficiency, which we already did for the zinc oxysulfide, where we had the best efficiency of 0.5%, thanks to the use of the C60 charge transport layer, which we are still improving further by playing with the charge transport layers and also bringing in ALD for the zinc oxysulfide. And more recently, we also played with bringing in amorphous silicon as an extra layer, giving us directly an efficiency of 0.5% in the case of the thickest amorphous silicon layer, which can still be improved, we believe. And also this AVT should be improved, we should be able to improve as well. And to our knowledge, all these results are very state-of-the-art as compared to the literature. And I just remember now, one thing I did not mention in the beginning, the JV curves for these UV selective cells, it's the solar spectrum has to be optimized because standard solar simulators are not optimized for the UVB part. So that's something we have been doing as well in this project. So you have to be very careful if you start to compare efficiencies in between papers, in between projects. But still, we're on track to get this 1% hopefully soon. So thank you for your attention, and I'm open for questions.
Okay, thank you very much, Bart, for nice presentation. There's a question from Luigi-Angelo Castriota. He comments, how do you manage to deposit the ITO on C60 BCP? If it's bad sputtering, what about reproducibility? And about C60, did you play with the thickness to find a good trade-off?
Wait, I'm also going to look at the question itself.
Yeah, it's in the
because I could
chat.
follow the first part, but I missed the second part. I'm not depositing the ITO myself, to be honest. So maybe we can also make an extra comment later on, an answer, because the person who is making the ITO is also here in the meeting. But I didn't hear any issues for the moment. So I don't think reproducibility-wise, we have that much issues for the moment.
I think I can complement this in the sense
Okay.
that one of the issues related, this C60 was deposited by, how is this called? Spinning, I think is.
Yeah.
And there is indeed a problem of uniformity of the layers. So this, we think that one of the problems we're having with these devices, in fact, is the lack of uniformity of the C60 layer. We are now analyzing other possibilities to deposit them even by evaporation, which is the other trick we are working on. Or the other thing is trying to replace the C60 by another inorganic transport layer. But C60, we think, is one of the main limitations that is leading us this limited efficiency value. I think is one of the things we're working optimizing, trying to go beyond the 1% of, okay, improving from 0.5% efficiency of the layers. To deposit the ITO on the C60, we didn't have, I don't remember, Alex commented in the labs having any issue related to this. I think the main issue was related to the uniformity of the C60 layer, I would say.
Yep. So you answered perfectly the second question.
Yeah, there's another question in the chat. Bart is.
Yeah, that's not a very clear question to me. Instead of sputtering, depositing the same materials as nanocrystalline particles to fabricate TPV would work. Do you have any comments on this view? not clear to me to what he's referring. Which of the three different approaches?
I would say it relates to the deposition of the absorber, our absorber, wide bandgap absorber layers. Right? Instead of using sputtering and reactive sputtering or sputtering plus
Yeah, but that's a
research and
scalability, yeah?
ionization.
So
Yeah.
our focus on sputtering related technologies is because of the scalability.
Yeah. I think that the answer maybe is that we essentially use the same industrial processes that are implemented in chalcogenide industrial technologies that essentially are working on sputtering, sequential processes, combining a sputtering of the precursors followed by reactive annealing to make the chalcogenide. There is the possibility also, of course, to make the position of the nanocrystalline particles, but then you have always the compromise to make some optimized recrystallization of the nanocrystalline particles to improve the crystalline quality of the layers. At the end, best results are obtained by sputtering, I would say.
I have a follow-up question on the C60.
Okay.
Yeah,
So,
sure.
C60 can contribute photocurrent itself, and so I wondered if you thought about the ability for C60 to contribute photocurrent and to contribute to the quantum efficiency curve, because it looks very similar. You can make a good C60 cell by itself, and it might be good. I don't know if you've done this, but have you looked at like not having the zinc oxysulfide component and just seeing if you're getting contribution from the C60 at all? Just one thing that can convolute and would be good to be aware of and check for.
Yeah, that's a very interesting comment. Really very interesting. Our impression now is that the main absorption in the UV is from the zinc oxosulfide layer, and C60 is contributing in very minor place. That's the reason we made very detailed QE measurements. But of course, we need to optimize the C60, and maybe that could help very much to improve the efficiency of the devices. That's fine. Yeah, really.
But maybe to add the S-kink we saw in the JV curve, we believe that might be related to C60, as has been seen for OPV as well.